Okay, so good evening, everyone. Today we have a pleasure to listen to the talk by Professor Sam Jaques. Sam made his undergrad at the University of Regina and master's degree Sam obtained here under the supervision of Alfred and Michele. And for the master's degree, Sam got Governor's General Gold Medal, and then with a scholarship moved for PhD studies to University of Oxford, and then joined back University of Waterloo as a faculty. So let us welcome Sam again.
Hi, thanks everyone for coming. So the talk that I will tell you about today is kind of addressing this question: how much does it cost to sort n integers? And this seems like a funny thing for a colloquium because we all know the answer to this, right? Anyone want to shout it out? N log n. And so that was a pretty quick colloquium. And in fact, this is, this dates back to, I looked this up, this is at least 1961. It's not even big, oh, it's theta. We know the matching lower bound from these information theoretic things. So since this is so well known, why am I interested in this problem? The thing is, my area is cryptography, and especially cryptanalysis. So the question is a particular cryptographic scheme hard enough to break that we can rely upon it for security? And right now there's a bit of a debate in post-quantum cryptography on two different parameters that would force us to have n 2 to the 90 or n 2 to the 132.
Why do you run it as exactly n log n? I mean, if the integers given you as bits, there's no information after that.
Sure. Replace integers with kind of an arbitrary list where you only have access to compare and swap. And I'm going to keep doing that. So I say integers to make it concrete. What you actually want to imagine is I've forbidden you to do anything more interesting than compare them and swap them. So the n that I'm thinking of are these sizes. And to put these into context, I was looking up, someone tried to estimate all of the data in all the computers all over the world today, and that's only 2 to the 75. So we're about over 1,000 times more data than we've ever produced ever. And then this one is kind of, you take, this is an estimate that John Skank produced. He was a student here a while back. Petabyte SD cards. And you start filling up everywhere with SD cards. You make a stack 120 meters tall, and you blanket the entire Earth with that. That's this much memory. So these are ridiculously large scales. And our question is, this is preposterous. That's totally safe. This one is huge, but could we get there? And this starts to be at a scale where this number doesn't make sense, because this is in the RAM model. So you've got one little processor that is capable of comparing and swapping, and a huge memory, and it makes one instruction to memory at a time. But if you've got this kind of memory, you're not going to just have one processor. So this leads to sort of this cryptographic perspective of different opportunity costs. And I'll say O of 1 bits of memory So there's some constant ratio between the number of bits of memory and one processor when I'm thinking about sort of the cost of this computer. There's a very silly sense in which this is true, which is that if I just go to Amazon right now and try to buy memory or buy a processor, the ratio of cost is independent of the size of problem I'm trying to solve. But in reality, this seems to work out. And if you look at modern supercomputers, the things that are training, say, ChatGPT, it's about 11 kilobytes of memory per processing unit in something like that, which remains fairly small. So our question is, anytime we have a computer, the cost that we're actually thinking of is kind of what else could we have built and what else could we have run? The opportunity cost of this algorithm. And that leads us to maybe start thinking about a hardware time cost. So we'll jump over here and sort of start. And this is exactly what the name is. Total hardware. Times total time. And if we think about any of our favorite sorting algorithms in the RAM model where you've got the one processor, then our hardware time cost is no longer n log n, because we have at least n hardware to store the integers, so it jumps up to n squared log n. And that's pretty bad. So the thing that I want to do is kind of go through different things that we could do to sort integers that are more optimal in this kind of computational model. Now this will also not be particularly exciting or new results. This also, a lot of these date back several decades, and kind of the pinnacle will be kind of a theorem that I haven't seen before that is fairly straightforward to prove. But mostly I want to kind of give a perspective on looking at algorithms in this way. And so first question is, can we parallelize any of our favorite sorting algorithms? And the answer for something like quicksort is yes. So I'm not going to go through this in a lot of detail. I'm going to give you just a sketch of what this looks like to get to more interesting things. And firstly, since we have our hardware cost lets us kind of equate bits of memory for one processor, what I can say is each processor I has one, let's call it xi, to sort. So we've got some list of n elements, and I'm assuming we have n processors and one element per processor. So what we can do is we can pick a random processor, let's say the first one, and let's say that x1 gets to be the pivot. So the way quicksort works is you compare everything to the pivot, move everything less than the pivot to the front, greater than the back, and then recurse. And this sorts a list. So the first thing we would naturally want to do is everyone wants to compare to that. And since they're all running in parallel, I can send the pivot to every one of these processors. And then they can all locally compare, is xi less than equal to pivot. And so they've all decided they want to be where their element should go. It should be in the front or the back. But they need to figure out where it should go. And what they can do for this is they can kind of talk to each other in sort of a binary tree structure. And what they're going to do with this is kind of ask, do you have something that is smaller than or greater than the pivot? And as they get further along, they ask how many elements above you are greater than the pivot, and how many elements below you are less than the pivot. And if you coalesce it in this tree and then sort of propagate the answer back down, again, I don't want to get too much into the details with this. You can end up with a situation where each processor knows three things, kind of if xi less than equal to pivot, number of xj less than equal to pivot, for j less than equal to I, and the number that are greater than the pivot. So it knows how many elements above it are greater than the pivot, how many elements below it are less than the pivot, and where its element should go. And that's enough information to kind of complete the kind of recursive case, because if it's less than the pivot, it knows this number, so it knows its element, if it stays in order, should just go to this location, the number that we have in step 2. So this processor can just say, my element goes to here. If it's greater than the pivot, it does the exact same thing, but in reverse. It knows how many sort of indices above it are greater than the pivot, so it would send it, let's say, here. And since they all have unique addresses, there's no contention among where they should go. They just send them all on their way. And we can sort of we can sketch out the time here. Sending out the pivot is O of 1 time because we send it all out. Potentially, there might be issues of how much data can you load on the wire at one time, but you could do a similar kind of binary tree to fan this out. Doing these additions is going to take a logarithmic number of steps. So we end up with logarithmic time for each list, and then a logarithmic number of recursions. O of log squared n. And the hardware cost, well, we only have n memory, we only have n processors, also O of n log squared n. But this is also incorrect, because there's a type of hardware that I have not included in my hardware cost here, that I've used a lot of to make this machine. Messaging, yeah. So what kind of hardware do we need for messaging?
Wires?
Mm-hmm. So how many wires does this machine have? Well, in this step where I kind of send all the messages around, they could have gone anywhere, right? For any different list, I'm going to have every processor be able to talk to every other one. So we actually need n choose 2, which is theta of n squared wires. So in fact, the hardware is n squared, and it's n squared log squared n again. So I'll throw this in the opportunity cost. O of 1 wires equals 1 processor. And again, it doesn't make, like, a wire seems very cheap. It seems like we should be able to build as many as we want. But when we're thinking about these scales, if we have 2 to the 90 processors, and we've got n squared, that's 2 to the 180 wires. This is the sort of thing where I think, you turn every atom in the sun into a wire, and you're not even close. So this architecture is ridiculous. And indeed, we're already at a scale, if you look at modern supercomputers, they are not all-to-all connected, because that would be too much wire. There's a whole field of research on how these things connect to each other. So can we come up with something better than this sort of parallel quicksort that I slapped together? And the answer is yes. This one is right. Atomic sequence. Oops. So I'm leaving out the fact that a Bytonic sequence is a sequence of n elements. But the thing that I want is that it decreases down to some point and then increases, or a cyclic shift of this. And I'll draw a picture to kind of illustrate what's going on here. Whoops. So I draw the value of the elements up here, and I draw the index, then it looks like that. Or some shift of it. So that might look like goes up to here, and then goes up to like that. The interesting thing about the shifts is that if I rotate this, and kind of the point where it wraps around is going to be in the middle of either an increasing or decreasing part. So I can draw a little dotted line that says the last element is necessarily less than the first element. And if I'd drawn it here, it would be the reverse, but either way, one of these properties holds. It turns out these are relatively easy to sort. And all I have to do is first I split the list in half. And so then just kind of go through the elements of each list, compare them and swap them to put the smaller elements in A and the bigger elements in B, and then sort the two sublists. And kind of another proof by picture on why this works. So let's say I start with some Bytonic sequence, and the left here is A, and the right is B. And so what I'm doing in step 2, you can think of as I've kind of stacked these together. I'm going to draw this so that this is a little more interesting. So this would be B, and this would be A. And since I'm comparing them kind of index by index, it's like I'm going through this and taking the smaller value and putting it in A, and the larger one putting it in B. So A becomes the minimum of this, and B becomes the maximum. So A becomes this, goes up and does that. And B becomes this. And the interesting thing here is that we have the same property where I cut this off at an increasing part. So if I do this dotted line, the first element of B is less than the last element of A. So A has that same property, and A is a Bytonic sequence. And kind of intuitively, this holds for any Bytonic sequence you have. I'm not going to prove this. And similarly, B is clearly a Bytonic sequence. The other interesting thing is because of these properties, every element in B is in fact greater than every element in A. And those two facts together mean that if I Bytonic sort them both, I've sorted the whole list. Because firstly, they're Bytonic sequences. So inductively, if this thing sorts Bytonic sequences, it sorts the subcases. And every element in B is greater than every one in A, so the whole list has kind of been partitioned in the right way. And the base case where these have 2 elements or 1 element is trivial. So what kind of times are we looking at? This is 0. This is just bookkeeping. This is 1 if I have the correct wires to do this. And so where are my wires? Processor I connects to, well, if I start, every processor needs to talk to one that is sort of n over 2 greater, because I'm taking, say, the third element in A with the third element in B, but I'm offset by that. Then when I recurse, I'm going to need to do I plus n over 4, I plus n over 8, all the way down to I plus 1. And assume n is a power of 2 just to make this nice, but it would work in general. And I'll say total log n wires. So this only has log n wires, so that's great. And it lets us do this step in one message. Sort of every sort of O of 1, I guess, if I include the compares and the messages. And then this is sort of the recursive case. So maybe I'll just say this is time of n over 2. And that gives me time of n is O of 1 equals, oops, I should put the big O. So this is the log n time. Now, the problem is it only sorts Bytonic sequences. But it's easy to transfer this into a sort for all kinds of sequences. And this is how you'd sort any list. All you have to do is split it into 2 halves, sort the 2 halves, but just sort the first half in reverse. And so naturally, if I've sorted two things, it looks exactly like this, because the first half is going down, the second half is going up. So I've made the bitonic sequence after step 2, and then this nice log time sort finishing things up. And if I think about the time of this, then I know that this is O of log n, and this will be kind of time to sort of n over 2, and this is time 0. So the sort time for n is log n plus the sort time of n over 2. And of course, I can sort these in parallel because it's a huge parallel machine. So I get O of log. I'm extremely happy with how the blackboards have worked out here because I can basically just modify this now. Okay, so this should give us our answer, right? We have hardware of O of n, time of O of log n squared. We're basically optimal. However, I claim that this has also ignored a critical hardware component that ruins the cost.
What's it's unrelated to your question. What's the guarantee that the minimum in A is smaller than or equal to the minimum in B?
In this one, the fact that the first element in A, the first element in B is greater than the last element in A, or that all of the elements after this step are less than all of the elements in B.
So and here you're getting from after step 2,
Yeah.
you're claiming that you have a bitonic sequence.
Yeah.
But your definition requires the minimum of A to be.
The minimum, this thing xk doesn't actually have to be the minimum in A, because I didn't require this to be exactly halfway through the sequence. So let's say that I have, this is A, and let's say that B, in fact, kind of looks like this. So A goes down here, and the minimum in B is a huge drop. I would let this value be xk. And I can just think of it almost, there's no guarantee that A has to be a nice shape of curve. It just needs to be decreasing. And so clearly it decreases up to xk and increases after, so it's bitonic. So yeah. Good? Great. Okay. Yeah, so bitonic sort, we get a bitonic sequence. It has this runtime, but I claim that the hardware of this machine is actually much more than O of n. And I'll erase this to kind of draw it out. So let's suppose that I draw.
Isn't it n log n wires?
Oh yeah, sorry. That's exactly right. Great, but I mean, I can I'll stack up as many logs as I want and kind of not worry about it. So this is roughly a sketch of a modern supercomputer, like I think Summit, no, it's Frontier, is the largest supercomputer right now, and it has these giant racks. So imagine each of these is the processors that are doing this sort. And I think about the connectivity I have. So I've got processor here, and it has one connection that's very close, then one that's twice as far away from that, and then twice as far from that. Then it starts having to go to other cabinets. And since the cabinets keep going, it goes like this. And the key fact is that this wire here is really long. And again, these are the kind of things that you don't think about. So I'm going to say O of 1 meters of wire equals 1 processor. And again, it's sort of a silly thing to start thinking about algorithms in terms of the number of meters of cable you're going to have to buy to build it. But again, at these scales, this actually starts to matter because a computer has a physical radius. You can't pack a computer into an infinitesimally small area. And so this pushes us into a regime of thinking about what is the actual physical geometry of the computer. So I'm going to have to work a little harder to define what I'm talking about. This is still going to be pretty sketchy. I'll just call this a machine. So I'm going to start with a graph, and I have all the integers from 1 to n as the vertices. Basically, each one represents a processor, and then some edges that are the wires between them. And I say it's directed basically so that I don't have to worry about two processors that want to talk to each other having to wait for the message. They just have separate channels. And strongly connected so every processor can send a message to any other processor. And I'm going to just say an embedding into d-dimensional space. I think this room is going to know better than I do a nice way to define this. But basically, all I want is, you put every processor somewhere, and you've made every edge into a continuous path between them, so that you can really think about what is the length of this wire. And an absolutely kind of critical thing that I need is I specify some minimum distance, and the processors have to be that minimum distance away from each other. I can't make infinitesimally small processors. And I'll sort of say the hardware of this machine is going to be something like this. So I take all of the edges, and they have some length, and I add up all those lengths. That gives me all of the wires in the computer. And I add that to the number of processors. And you can also, I can ignore this, because necessarily, I'm going to have at least one wire per processor. I have some sort of spanning tree, and the lengths are all at some minimum value. So this term is already omega of n, but just for completeness. And I'll assume that each of these machines has some constant amount of memory. And I'm going to kind of very sketchily define what it means to compute on this machine. Formalizing computers and their programs is annoying. So just kind of, I hope you understand what I mean by this definition. I'll just say it's t time steps in which so each processor is working independently. And what can it do? Let's just say, one sort of operations. So pick your favorite instruction set. It can do a constant number of operations. And I'll say load or send 1 bits on an incident edge. So what I'm imagining is that the processor in each one of these time steps can put some number of bits on the edge, and then in the next time step, wherever that edge goes to, can then read that data off of the wire. And if it doesn't read it, it's deleted so that the other processor can keep sending data. And I'll expand this to load send 1 element of, and I'll just, in all caps, call this the list, as in the list to be sorted. So I'm treating the elements of this list not as integers, as in fact their own distinct object, that can't be treated just as bits. And I'll say compare / copy O of 1. So this is avoiding exactly this problem where maybe you can do some sort of integer compression or something. I want to say you can only compare and swap. Because my goal with all of this is defining this in such a way that I can show that there is actually a lower bound on the hardware time cost of sorting based on the geometry of the computer. And so having laid down what this all is, the theorem to prove, sort of for all, well, maybe that's a, I'll include the kind of counting argument in a sublemma. Sorting has, using an abbreviation for hardware time cost, n to the 1 plus 1 over d plus little o of 1. So the little o means that this thing goes to 0 as n increases. So it's not a constant, it goes to 0. So that lets me hide all logarithmic factors, all constant factors in n, and leaving the main thing that I care about, which is n times basically the radius of the machine, n to the 1 over d. Because if you're trying to put these processors in d-dimensional space, they will have a physical radius proportional to n to the 1 over d. And this, for 2 dimensions, in fact, it's kind of well known that this is a, and having this little o of 1 makes it necessarily an upper and lower bound. There's kind of this idea of a mesh sort, where you have a grid of processors that only talk to their nearest neighbors. And that one, it's easy to show this for. There's, well, easy to show the lower bound because there's literally the number of steps to go from one side to the other is the square root of the size of memory. Showing that you can sort in square root n time is more difficult, but it can be done. But I'm interested in the case of, well, let's say that I don't just have a mesh machine. I'm allowed to kind of throw on some extra wires. Can I make this any faster? And the answer turns out to be no. So what I'm going to do is define some function of the sort in the computer that I'll just call d. So I'm going to sum over all time steps, and I'm going to sum over all edges, and length of e if e has some xi. So what I mean is that according to these instructions, in every step, it's a reasonably well-defined thing to ask, is there a particular element of the list on this wire at this time? And if there is, I add the length of wire, and then I add that up over all the time steps. So it's kind of like how many, the length and the time that the wires are occupied with sending messages around from the list. And it's pretty easy to see that this is already a lower bound on the hardware time cost, because this thing here is at most the, I didn't give this a variable. Let's just say I call this W for the length of all the wires. This thing here is necessarily the length of all the wires, and I add this up over all the time. So this has to be a lower bound on the hardware time cost. And I want to show that it has the lower bound that I've given there. And in fact, I'm going to do a little better and show that this is for most sorts. So I'll maybe say for all, but O of 1 over n sorts. So what I mean is if you give me a list at random in all but this negligible fraction of cases, it's going to be this hard to sort. So how I can show that is I can rewrite this sum as in fact saying how do I want to say this? Length, sort of all e with xi So I'm just kind of, I'm switching the way that I do the sum to sum over the elements of the list. So at any given time, which wires contain that element, I add that all up. And I'll maybe define this to be, let's call it Li, and that'll make things easier. So I add that up over all the time steps. My question is, so sort of let S of epsilon equal all lists So I'm going to make the list of all the set of all the lists that can be sorted where this number is actually relatively small. So I've got some epsilon greater than 0, and I'm just saying that they can be sorted less than that. And what I want to do first is pick some L, and then for S and S epsilon. So when I'm talking about a sort, really what I mean is kind of a list. Because every list that I give it is going to define some set of operations that have to be done to sort it. And so I think what's actually going to happen to put these all together. So, if I have some list of integers and I can just kind of move one a little bit without changing the ordering in which they have to be sorted, I count that as the same sort. So really I can identify all my sorts by permutations, because what the computer is going to compute is some permutation of the input. And for each of these sorts, what am I trying to say here? This is a where for n. So I want to further partition this into all the sorts where I have exactly n elements that have to travel a total distance greater than some L. So I want to split the sort, I've got my sort, and I want to split the list into elements that aren't going very far and elements that are going quite far. And then I want to count this. Okay, so how large can this set be? Well, first I need to choose which elements are going to actually go very far. So I add on a big and choose n. And then I think about the elements that do travel a distance more than L. I don't really have any restrictions that I can think of that I would put on those. So basically I'm left choosing kind of, I have some element I, it could go anywhere. And n to the n is a big overestimate of that, but that'll actually be fine. Then I'm left on the number of choices for where the elements that don't go very far go. So I've got something that can't go very far, so I'll sort of leave this as a blank and kind of derive what it has to be. First, L of I j if xi goes to processor j. So really, the physical distance between two processors is an upper bound on the total length the message has to go. And you can kind of see this because I've defined this graph. If the sort has to take the element from processor I to processor j, then it basically has to travel along all of these wires to get there. And that's going to create a continuous path, and the triangle inequality just trivially gives us this. And then so this means that the total number of processors, the total number of locations that I could take the ith list element and send it to is going to be bounded by how many processors are at the distance L. So kind of number of processors, within L And I'm going to just say that this is L to the D, big O of L to the D. The reason for that is I'm in d-dimensional space. So I've got some d-dimensional ball, and that's the volume that has to contain all of the processors. And the volume of that ball is L to the D, because it's in d dimensions. And because of this critical requirement, that the processors have this finite size, then for every processor, there's a finite sized ball around it that has some finite volume. So if I literally just divide the total volume within distance L by this finite volume, I get O of L to the D. And that's an upper bound on how many processors I could possibly fit in that region. So when I'm thinking about trying to construct a list and count it, where these elements only go a distance L, the thing that goes over here is I only have L to the D processors to choose from for the remaining n minus n messages. So I can upper bound the number of these sorts like that. And so clearly this is the sum from n equals 0 to, I'll call it n max, of, and I'm going to claim that this is increasing in n. So I get to just say n max times I'm writing pretty, not very messy here, or very messy there. But this is kind of the interesting part is laying this out. The rest of it basically becomes arithmetic once we get this question of n max. So basically, what's the maximum number of elements in this list where they're traveling a distance at least L? And this is where we bring in the value D, which for this particular set, really made myself walk here, is bounded by this value. So I know that D is greater than this, so I'll write that down. And this is necessarily going to be n max times L. So if I take the maximum number of messages that I could have that travel a distance at most L and multiply them by L, that's going to be a lower bound on kind of the sum of the distances all the messages travel. And so what I can do is set L to be 1 over d minus epsilon over 2. And so n max is this. So kind of, it's close to all of the elements, but it's a epsilon over 2 fraction away from them. And this, then you can do a bunch of annoying arithmetic, and you get, I think, something of this nature. N log n plus O of n. So it's almost n log n, but we have this little extra term. And the thing is, the total sorts, total number of possible sorts that I could have is n factorial, right? It's the number of permutations. And this, of course, is n log n plus O of n. N log n is the leading term. And so if I think about the fraction of sorts where this d is bounded by this as a fraction of the total sorts, I divide them, which means subtracting the exponent, which cuts off the n. So therefore, you're not going to see that if I duck down. So the fraction of sorts that have distance bounded by this is at most this tiny, actually very quickly decreasing fraction. So this tells me that this gives the result, basically. Because I've said for most sorts, you're actually going to have d greater than n to the 1 plus d minus epsilon for any epsilon. And I've already said here that kind of trivially d is the lower bound on the hardware time cost. And so that gives me that for all but a tiny fraction of sorts, you have sorting have this, this cost. And not a fairly straightforward kind of counting argument proof. And this kind of gets us to the big conclusion. This is our cost. What is d in practice? It's got to be at least, or at most 3, because we live in 3-dimensional space. I can't have a 4-dimensional computer. And in practice, d is basically 2 because of heat dissipation concerns. So you have this square cube law that if I make a giant cube or sphere of computers and I try to cool them because they produce waste heat by doing computations, that waste heat also has to leave through the area, which is only growing with the square of the radius, while the number of computers is growing with the cube. And again, in practice, d seems to be 2 for most actual big computers. So that means that sorting has a cost of basically n to the 3 halves. So I'll maybe write this right at the start of the talk. N to the 3 halves. And maybe you could say d is a little bit larger. Maybe you get 1 plus epsilon. And this is quite an interesting result for the cryptographic point of view. Because if I take 3 halves times 90, I get, what is that, 135? That is largely considered secure. If you have something that takes 2 to the 135 operations or cost in some sense, this is never going to break. And the research question that this has kind of led to is, what does that mean for the algorithms where this is actually just a subroutine? So attacking modern post-quantum cryptography, you have these algorithms that do a lot of extra interesting thing with high-dimensional lattices and vectors, but at some point they have to sort a big list of vectors. And so that sort takes 2 to the 135 cost. That adds to the cost of the whole algorithm compared to if you analyzed it in the RAM model. And so you might think, okay, take the RAM model cost and just add 45 bits to the security. Just tack on a plus 45. But the interesting thing is that once you switch to this different computational model where sorting has this extra cost, the thing that you want to do is change the algorithm that you use. So as a subroutine of this larger cryptographic attack, you want to be pulling as much cost away from the sort as possible. You want to be doing as much work in other steps so that you have as few sorts that you need to do. And so the thing that I've been working on is actually amortizing this away so that even though you're adding a 2 to the 35 factor to the cost of each sort, the cost of the overall algorithm compared to in the RAM model is only going up by about maybe 10 to 20 bits, where a bit is kind of the numbers in these exponent. So that's kind of the result that I've been working on. Hopefully this gave you a window into the cryptanalyst view of algorithms and computers. I'm happy to take any questions.
Okay, so just coming back to the original thing, like you assume only comparisons. In real life, you probably sort numbers that are much nicer than just comparisons ones. What's about how secure is that then? Yeah,
so in the cryptographic case, you're not sorting integers. What you're sorting is data where you have a big vector, and then you have kind of a locality-sensitive hash of the vector. So the thing that you're working with seems to be kind of fairly random, so I don't know that you could do much better than these. The hope is that this entire list basically looks random and you can't do anything extra, because if you could, then kind of that adds extra structure to the whole problem and then suggests that maybe there's actually whole other avenues of attack besides this lattice fitting. So it's sort of a foundational assumption is that these things look random, and that's why you have to do the algorithm the way it is. And then that kind of says, okay, you're not going to do much better than a general purpose sort.
Are there any other questions? Okay, so let us do that offline. Thanks.